Hello everyone, today I would like to present our work sewer tape, a transfer-based technique to help fabricate circuits on a wide range of materials for versatile real-world purposes. My name is Tingyu Cheng, currently a PhD student at the Georgia Institute of Technology, supervised by Professor Hyunjoo and Gregory Abowd, and I am very honored to present this work on behalf of our team. This work is also a collaboration among Georgia Tech, University of Tokyo, and Carnegie Mellon University. In the past decade, digital fabrication tools such as laser cutters, 3D printers, or CNC routers have benefited not only manufacturers but also researchers, makers, or even children to fabricate their own designs rapidly. At the same time, these tools allow users to play with a wide range of materials. For example, 3D printer can print plastics, polymers, or even food ingredients in an easy, fast, and compact way. Our motivation here is to further extend the benefits of digital fabrication to make electronics with an accessible fabrication process and a diverse material selections at the same time. Researchers have already introduced works for digital fabrication of electronics in HCI and the ubiquitous computing fields. For example, like inkjet printing, screen printing, or even 3D printing. Among all of these methods, inkjet printing is showing the brightest future due to its great ink conductivity and the compact fabrication process. For example, instant print circuits use the commodity inkjet printer and the silver nanoparticle inks to print conductive traces. While for ink, there are two main curing methods, which require either heat sintering or chemical sintering process as post-treatments. The heat sintering has drawbacks of requiring actual heating tools and can potentially damage the printing substrates, so the chemical sintering process shows a brighter future, since there is almost no requirements for the post-treatments. However, conventional chemical sintering process has been limited to the specially coated paper or PET film. This substrate limitation has heavily restricted people's design choices. Here we propose sewer tape, which is leveraging the existing printed circuits techniques by simply transferring the printed circuits to a wide range of adhesive materials with different purposes: transparent, ultra-flexible, heat-resistive, or even water-soluble. In the following of this presentation, I will mainly discuss in more details about the fabrication process, testing results, and applications. The fabrication has three simple steps: printing, transferring, and assembling. For printing, similar as most of the inkjet printing circuit methods, we just need to load the conductive nanoparticle ink to the inkjet printer and print our design. For the transfer step, we need to simply apply the targeting adhesive substrates to peel off the printed pattern achieved from the printing step. After the transfer, we can mount the electronic components with conductive glues or adhesives. For the transfer step, we would like to highlight the retransferability of our technique, where the conventional printed traces can be easily scratched and hard to repair. While for our transfer technique, we can simply retransfer a new trace on the damaged spot, as here we are demonstrating a retransfer of a conductive trace to light up an LED. For the testing, we have done a thorough study for what substrates we can transfer from and what substrates we can transfer to. For the substrate that we can transfer from, most of the commodity photo papers and the Mitsubishi PET film exhibit successful transferability and perform fairly good conductivity after the transfer. For the substrates we can transfer to, we have searched and tested most of the tapes and the commonly used adhesive materials in the market to evaluate the electrical performance after the transfer. Most of the materials show promising conductivity and indicated a peeling force from 0.3 Newton per centimeter to 6 Newton per centimeter would be proper to transfer. We also tested 7 different materials and 3 different geometries to exemplify most of the daily surfaces or objects that we can apply the transfer the conductive trace to. Enabled by our sewer tape, we can fabricate functional circuits for different purposes. We can simply transfer the pattern to heat-resistive Kapton tape to fabricate a temperature sensor, which cannot be achieved by the conventional photo paper or PET substrates. Or we can directly transfer a conductive pattern onto a soft robotic material to rapidly fabricate a bending sensor for soft robots. We also demonstrated a flexible multi-layer LED which is powered wirelessly. We can also transfer a pattern onto Scotch tape to make a flexible extension panel for mobile devices. The transfer technique also has a modular nature, which allow people to transfer different patterns onto the same substrates one by one. Here we demonstrated 7 Christmas tree patterns are transferred separately onto a single sheet of PDMS sheet, where the modular nature also enable a fabrication dimension beyond the conventional printing paper. You can also check our paper to see more technical details, and I would like to thank for all the team members and supervisors again for their support and efforts.